Hey, welcome back to graph theory. In this video, we're going to continue discussing inequalities. In particular, we're going to focus on one very powerful inequality, which is called Jensen's inequality. We started discussing inequalities in the last video. In that video, we went over two inequalities in particular. We started with the trivial inequality. This one might have seemed really obvious. It says for any real number x, we have x squared is greater than or equal to 0, and we only get the equality case if and only if x is equal to 0. We use the trivial inequality to prove the Cauchy-Schwarz inequality. And the Cauchy-Schwarz inequality says that if we have two sequences of real numbers, which we write as a1, a2 up to an, and b1, b2 up to bn, then the product of the sums from I equal 1 to n of ai squared and from I equal 1 to n of bi squared is greater than or equal to the square of the sum from I equals 1 to n of ai bi. Another way to say the Cauchy-Schwarz inequality is if we represent the sequence a1, a2 up to an as a vector u, and the sequence b1, b2 up to bn as a vector v. And the inequality is saying that the absolute value of the dot product of u and v is at most the product of the magnitudes of u and v. So we prove that using the trivial inequality. And we get equality for the Cauchy-Schwarz inequality if and only if there exists some real number r such that the sequence a1, a2 up to an is equal to r times the sequence b1, b2 up to bn. Another way to say that is that the vectors u and v are parallel to each other. Another thing that we saw in the last video was a proof of the fact that the Turan extremal function of the complete graph of order r is at most r minus 2 times n squared over 2r minus 2. In this video, we're going to look at more Turan problems. Instead of looking at complete graphs, we'll look at complete bipartite graphs this time. And we're actually going to be able to prove the best known upper bound on the Turan extremal function for complete bipartite graphs. And when I say best, I mean best up to a constant factor. So our bounds will be big O bounds. We won't really care about constant factors. And the main tool that we'll be using throughout this whole video is Jensen's inequality. Before we state Jensen's inequality, we need to define a couple of things. First, let's define convex functions. So suppose that big X is a connected subset of the real line, so X is an interval, and let F be a function from X to the reals. And we're going to define F to be convex if for all real numbers x1 and x2 in big X, and for all real numbers t in the closed interval from 0 to 1, we have f of t times x1 plus 1 minus t times x2 is less than or equal to t times f of x1 plus 1 minus t times f of x2. And another way to look at the definition of convexity is to say that f is convex if the line segment between any 2 points on the graph of f lies above the graph between the 2 points. So we can see a picture to see why this makes sense. We consider the graph of some f over here. And over here we'll have another f that we'll consider second. Both of these are defined on some interval of the real line. So they're not defined on the whole real line. Otherwise I would have had to draw them going off forever. But some interval, and it's a connected subset of the real line. So the function on the left, if I look at any 2 points on the graph of that function, I can call them x1, f of x1, and over here I have x2, f of x2, and I can take the segment between those points. And we can see that for any 2 points I choose on this graph, if I draw the segment, it's always going to be above the graph of the function between the points. So the function I drew over here is convex. The function over here, in some places, I can choose 2 points, and the segment between the points will be above my graph. But in other places, I choose 2 points, and the segment is below the graph. So this one would not be convex. In the definition of convexity that we see in the second bullet point, the first part of the inequality, the left side, as t ranges from 0 to 1, that left side goes from here along the graph of our function to here. So it just stays along the graph of our function. The right side as t goes from 0 to 1, it goes from here to here. And both of these sides, we're only looking at the y values in that graph. So we're ignoring the x values. The x values will be tx1 plus 1 minus tx2 for t ranging from 0 to 1. So we see that it makes sense here. For convexity, we want the left part, the graph part, to be below the right part, which is the segment part. Now that we saw convexity, let's look at concavity, which we can view very similarly, but flipped. So for concave functions, again, let x be a connected subset of the real line, and let f be a function from x to the reals. And we'll define f to be concave if for all real numbers x1, x2, and x, and for all reals t in the closed interval from 0 to 1, we have f of t times x1 plus 1 minus t times x2 is greater than or equal to t times f of x1 plus 1 minus t times f of x2. Notice here, this is almost the same definition we saw with convexity. It's just that the inequality flipped. So in terms of line segments, instead of the line segment being above the graph between the 2 points, we want the line segment to be below the graph between the 2 points if we're talking about a concave function. So we can look at some examples. On the left, we'll have a function like this. On the right, we'll have a function like this. On the left, if we look at any 2 points, the segment between those points is going to lie below our graph. So this one is concave. On the right, there's some places where the segment is going to lie above the graph. So this one would be not concave. And we can see how the definition in the second bullet compares to our way of viewing it with segments. So the left part of the inequality, as t goes from 0 to 1, if our x1's over here and our x2 is here, then that left part is going from here to here, and the right part is going from here to here along the segment. And so we want that left part to be greater than or equal to the right part. So we want the part along the function f to be above the part along the segment. Now that we saw the definitions of convex and concave functions, we're ready to state Jensen's inequality. So let's start with Jensen's inequality for convex functions. Again, we'll have x be a connected subset of the real line, and f will be a function from x to the reals. And Jensen's inequality says that if f is convex, and if x1, x2 up to xn are real numbers in the set big X, and if a1, a2 up to an are positive real numbers, then if we take f with the input of the sum from I equals 1 to n of aixi over the sum from I equals 1 to n of ai, this is going to be less than or equal to the sum from I equals 1 to n of ai times f of xi over the sum from I equals 1 to n of ai. And this is going to generalize the idea about the line segments between any 2 points being above the graph. In the case that n equals 2, it's the exact same as the definition of convexity. Now for concave functions, the statement of Jensen's inequality will be very similar. It's just going to have the inequality flipped. So the setup will be the same. We'll have a connected subset x of the real line, and f will be a function from x to the reals. And Jensen's inequality for concave functions says that if f is concave, if x1, x2 up to xn are real numbers in big X, and if a1, a2 up to an are positive real numbers, then if we take f with the input sum from I equals 1 to n of aixi divided by sum I equals 1 to n of ai, this is going to be greater than or equal to the same thing that we saw on the previous slide, just the sum from I equals 1 to n of ai times f of xi divided by the sum from I equals 1 to n of ai. And like the previous slide, this generalizes what we see with the definition of concavity. So it generalizes the idea of the graph being above the segment. So let's prove Jensen's inequality for convex functions. And we won't prove it for concave functions because the proof for concave functions is nearly the same as the proof for convex functions. It just has the inequalities reversed. So let x, again, be that connected subset of the real line. Let f be a function from x to the reals. Suppose that f is convex. Suppose that x1, x2 up to xn are real numbers in big X. And suppose that a1, a2 up to an are positive real numbers. And we want to prove Jensen's inequality, which is this statement about f of this ratio of sums being less than or equal to the sum of the f's over the sum in the denominator of the ratio of the left side. So we're going to try to prove Jensen's inequality. In order to prove it, we're going to use induction on n. We're going to start with n equals 2. N equals 2, like we mentioned on the previous slide, follows immediately from the definition of convexity. In particular, the parameter t and the definition of convexity, we can use t equals a1 over a1 plus a2, and we see that if we calculate 1 minus a1 over a1 plus a2, in other words 1 minus t, that gives us a2 over a1 plus a2. And so we get the statement of Jensen's inequality for n equals 2 just from the definition of convexity, which must be true for f because it's convex. Now, since we proved the base case, what's left is to prove the inductive step. So we will suppose that Jensen's inequality is true for n equals k. And now we need to prove that it's true for n equals k plus 1. So we'll suppose that x1, x2 up to x of k plus 1 are real numbers in big X. And we'll suppose that a1, a2 up to a sub k plus 1 are positive real numbers. So we're going to define these other numbers, b, j, and they'll be equal to aj divided by the sum from I equals 1 to k plus 1 of ai. So by definition, the sum of the bj's is equal to 1. By the convexity of f, we can get an inequality. And this inequality is going to get us most of the way to proving this inductive step for Jensen's inequality. Before we apply the convexity, we will first rearrange the left side of Jensen's inequality. So we start with the left side of Jensen's inequality, which is f of the sum from I equals 1 to n of ai xi over the sum from I equals 1 to n of ai. So this is what we see in the left side of the second bullet. And if we write that in terms of bi's, we can write that as f of the sum from I equals 1 to k plus 1 of bi xi, because in this case we're proving it for n equals k plus 1. We can rearrange the terms inside the f. So we can write that as f of b1 x1 plus the sum from I equals 2 to k plus 1 of bi xi. The sum from I equals 2 to k plus 1 of bi xi, we can write that as 1 minus b1 times the sum from I equals 2 to k plus 1 of bi over 1 minus b1 times xi. Why would we do that? Well, it's so that we'll have a b1 and a 1 minus b1. And that lets us apply the convexity of f. So using convexity, we get that f of b1 x1 plus 1 minus b1 times that sum is less than or equal to b1 times f of x1 plus 1 minus b1 times f of the sum. And at this point, we can take f of the sum and we can apply our inductive hypothesis. And our inductive hypothesis was for n equals k. And our sum there has k terms, so it's fine. By the inductive hypothesis, we can say that f of the sum is less than or equal to the sum from I equals 2 to k plus 1 of bi over 1 minus b1 times f of xi. And we can combine everything now. So we get that f of the sum from I equals 1 to k plus 1 of bixi is less than or equal to b1 times f of x1 plus the sum from I equals 2 to k plus 1 of bi times f of xi. And we can rewrite that in terms of the AIs. And it gives us exactly the right side of the Jensen's inequality that we were trying to prove. So we just proved Jensen's inequality. And like I said before, for the concave function version of Jensen's inequality, the proof is very similar, so there's no need to repeat the details. So we're going to see some examples of applications of Jensen's inequality. When we use these applications, we're going to apply Jensen's inequality to certain functions f. We're not going to want to have to prove that f is convex or concave using the definitions of convexity and concavity that we saw on the earlier slides. We're going to want to use an easier way. And you probably saw this way before in some calculus classes. So if we want to check convexity, we can check second derivatives. And here's a problem for you. Suppose that f from x to the reals is twice differentiable on all of x. Prove that f is convex on x if and only if the second derivative of f is greater than or equal to 0 for all of big X. And I claim that an analogous proof to the one for that problem shows that f is concave on x if and only if the second derivative of f is less than or equal to 0 for all of big X. So if we want to use Jensen's inequality and we want to check whether some function is convex or concave on some interval x of the real line, all we have to do is check the second derivative of that function on the interval that we care about. Now we're going to apply Jensen's inequality to prove some other inequalities. We're going to start with what we'll call the general AMGM inequality, even though we'll see a more general version of it on the next slide. We already saw the two-variable AMGM inequality. The more general one, which is stated here, says that if x1, x2, up to xn are positive real numbers, then the sum from I equals 1 to n of xi divided by n is greater than or equal to the product from I equals 1 to n of xi raised to the 1 over n. In other words, the arithmetic mean of the xi's is greater than or equal to the geometric mean of the xi's. In order to prove this result, we can use Jensen's inequality, and we'll apply it to the function f of x equals log base e of x. If we want to calculate the second derivative, we find the first derivative is 1 over x, and the second derivative is thus minus 1 over x squared. And this is less than 0 for all x greater than 0. So we can conclude that f is concave on the open interval from 0 to infinity. So we can apply the concave function version of Jensen's inequality. We can apply it with equal weights, a1, a2, up to an, all equal to 1 over n. And that gives us that log base e of the sum from I equals 1 to n of xi over n is greater than or equal to, because this is the concave version, it's greater than or equal to the sum from I equals 1 to n of log of xi divided by n. We can take e to the exponent of both sides of this. So we raise e to the power of both sides, and that gives us that the sum from I equals 1 to n of xi over n is greater than or equal to the nth root of e to the sum from I equals 1 to n of log of xi, and that simplifies to the product from I equals 1 to n of xi raised to the 1 over n. And that's exactly what we wanted to prove. So that gives us the general AMGM inequality. But we can actually prove a more general version where we, instead of using equal weights, all equal to 1 over n, we allow any weights. So we call that the weighted AMGM inequality. And if x1, x2 up to xn are positive real numbers, and w1, w2 up to wn are positive real numbers which sum to 1, then we can say that the sum from I equals 1 to n of wi xi is greater than or equal to the product from I equals 1 to n of xi to the wi. We're going to prove this almost the exact same way as the previous slide. We're going to use the same function, f of x equals log base e of x. The function is concave on the open interval from 0 to infinity. So we'll use Jensen's inequality. This time, we'll have the weights be the wi's instead of 1 over n. And this gives us that log of the sum from I equals 1 to n of wi xi is greater than or equal to the sum from I equals 1 to n of wi times log of xi. We'll do the same thing we did on the previous slide. We'll raise e to the power of both sides. And that gives us the sum from I equals 1 to n of wi xi is greater than or equal to e to the sum from I equals 1 to n of wi times log of xi. And that simplifies to the product from I equals 1 to n of xi to the wi. So that's the weighted AMGM. Before we prove more inequalities using Jensen's inequality, let's look at an example of how we can use the AMGM inequality. So suppose that A, B, and C are positive real numbers, any positive real numbers, and we want to see why is it true that the product a squared b plus b squared c plus c squared a times ab squared plus bc squared plus ca squared, why is it that that product is greater than or equal to 9 times a squared b squared c squared? We can prove this very quickly using the AMGM inequality. We apply AMGM, the 3-variable version of it, to the first term in the product. And we can write that a squared b plus b squared c plus c squared a over 3 is greater than or equal to a squared b times b squared c times c squared a raised to the 1/3. And this gives us ABC. Similarly, if we apply AMGM to the second term in the product, we get AB squared plus BC squared plus CA squared over 3 is greater than or equal to the product AB squared times BC squared times CA squared raised to the 1/3, again, which gives us ABC. We can take both of those last two bullets and multiply both sides by 3. That implies that when we take the product of the two terms on the left, a squared b plus b squared c plus c squared a times ab squared plus bc squared plus ca squared, we get that that is greater than or equal to the square of 3abc. And that gives us 9 a squared b squared c squared. And that's exactly what we wanted to prove. So AMGM solved that problem pretty quickly. Here's a problem for you to think about. This problem uses one of the inequalities that we have discussed recently. Suppose that f is a real polynomial with positive coefficients. Prove that if it is true that f of 1 over x is greater than or equal to 1 over f of x at x equals 1, then it must be true that f of 1 over x is greater than or equal to 1 over f of x for all x greater than 0. So for all positive x, that inequality must be true, as long as it's true at x equals 1. We're going to use Jensen's inequality to prove another well-known inequality. And this inequality, we'll see it applied in some other problems in extremal graph theory later in the class. This inequality is called the power mean inequality. Suppose that we have real numbers x1, x2, up to xn. They're all positive. And suppose that w1, w2, up to wn are positive real numbers which sum to 1. Suppose further that p and q are real numbers with 0 less than p less than q. Then the power mean inequality says that the sum from I equals 1 to n of wi times xi to the p raised to the 1 over p power is less than or equal to the sum from I equals 1 to n of wi times xi to the q raised to the 1 over q power. So notice that the difference between the left side and the right side here is that the p's got replaced with q's. That's the only difference. So the claim is that if both p and q are positive and p is smaller than q, then the version with the p's is less than or equal to the version with the q's. And we're going to prove that using Jensen's inequality. We just need to choose a function that will help us prove it. So the function we'll use is f of x equals x to the p over q. Let's check that function. When we take its first derivative, we get p over q times x to the p over q minus 1. When we take the second derivative, we get p over q times p over q minus 1 times x to the p over q minus 2. And we can see that this is less than 0 because p over q is positive, but p over q minus 1 is negative since q is greater than p is greater than 0. So that tells us that f is concave on the open interval from 0 to infinity, since the second derivative is less than 0 when x is positive. So since f is concave on that open interval, we can apply Jensen's inequality, the concave version of it, on that open interval. And when we apply it with the weights AI equal to WI for each I, we get that f of the sum from I equals 1 to n of WI times xi to the q is greater than or equal to the sum from I equals 1 to n of WI times f of xi to the q. So we can use the definition of f here. And when we use the definition, that gives us that the sum from I equals 1 to n of WI times xi to the q raised to the p over q power. This is because f of x equals x to the p over q. That's going to be greater than or equal to the sum from I equals 1 to n of WI times xi to the p. And that's because f of xi to the q equals xi to the p. Now, we can take both sides and we can just raise them to the 1 over p power. When we do that, the left side becomes the sum from I equals 1 to n of WI times xi to the q raised just to the 1 over q. And the right side becomes the sum from I equals 1 to n of WI times xi to the p raised to the 1 over p. And that was all we wanted to prove. So that's the power mean inequality. And now we're going to see how to apply Jensen's inequality for bounding some Turan extremal functions. So before we get to a specific extremal function, recall that we defined a graph to be H-free if no subgraph is isomorphic to H. And we defined this extremal function, the Turan extremal function, Ex of NH, to be the maximum number of edges in an H-free graph with n vertices. And in the last video, we saw how to prove sharp upper bounds on the extremal function of the forbidden complete graph of order R. So we proved upper bounds using a short induction argument, which was published by Staten. And we saw lower bounds for this extremal function in class. The lower bounds were some graphs that we constructed. So we're going to focus for the rest of this video on Turan extremal functions for complete bipartite graphs. Before we get to more general complete bipartite graphs, here's a problem for you to think about. When n is divisible by k, can you find the exact value of the Turan extremal function of n comma k 1 comma k, where again k 1 comma k is the complete bipartite graph with parts of size 1 and k. We also call that a star. So to prove the more general bound, the upper bound on the Turan extremal function of complete bipartite graphs whose parts both have size at least 2, we're going to use Jensen's inequality. The bound that we're going to prove is the Turan extremal function of n comma krs is big O of n to the 2 minus 1 over s. In other words, there exists some constant c such that we can bound that Turan extremal function with an upper bound of c times n to the 2 minus 1 over s. So we already know binomial coefficients, what their definitions are. It's going to be useful for this problem to generalize the definition of a binomial coefficient from integers to real numbers. We will define x choose s for a real number x and some positive integer s to be equal to the product x times x minus 1 times x minus 2 down to x minus s plus 1, and then divide that by s factorial. And it will equal that as long as x is greater than or equal to s minus 1. Whenever x is less than s minus 1, we will define it to be equal to 0. So here's a problem for you to think about. Prove that the function f of x defined as x choose s is a convex function. And prove that it's convex for any real number. So prove it's convex on the whole real line. We don't even necessarily need that it's convex on the whole real line for the next proof. We only need that it's convex on the open interval from 0 to infinity. But either way, you can prove it. So let's prove the bound that we claimed is true. We'll suppose that we have some graph G, which has vertex set V and edge set E, and G is KRS free, and G has n vertices. We'll name the vertices V1, V2 up to Vn, and we'll define di for each I from 1 up to n as the degree of the vertex Vi. We're going to count the number of copies of the star K1s in this graph G in 2 ways. And it's going to help us get the upper bound that we're looking for. We'll let P be the number of copies of K1s. First, we can see that we can count P by looking at each vertex in our graph as the center of the star. And when we count P that way, we can see that P is equal to the sum from I equals 1 to n of di choose s, because there will be di choose s ways to choose the s leaves of the star. However, we can also count a different way. We can use the fact that G has no copy of KRS in it. It's KRS free. And that tells us that P is less than or equal to R minus 1 times n choose s. If P was greater than or equal to R minus 1 times n choose s plus 1, by the pigeonhole principle, there would exist R vertices with the same s neighbors in G, and that would give us a copy of KRS, and that would contradict that G is KRS free. So that's why we get this upper bound of P is less than or equal to R minus 1 times n choose s. We're going to define this number D to equal 2 times the cardinality of E over n. In other words, 2 times the number of edges in G over n. And we can write that as the sum from I equals 1 to n of di divided by n. That's because the sum of the degrees in G is equal to twice the number of edges. Here's where we can apply Jensen's inequality. We can use the fact that D choose S is equal to 2E, 2 times the cardinality of E over n choose S. And we can write that as the sum from I equals 1 to n of di over n, choose S. And then here is where we apply the Jensen's inequality. So using the fact that we saw that the function x choose S is a convex function, that was the problem on the previous slide at least, we can conclude that the sum from I equals 1 to n of di divided by n, choose S, is less than or equal to the sum from I equals 1 to n of di choose S, all divided by n. And we can look back at the third bullet, and we saw that p was equal to the sum from I equals 1 to n of di choose S. So we can rewrite the sum from I equals 1 to n of di choose S over n as p over n. And we know from the fourth bullet that p over n is less than or equal to r minus 1 times n choose S over n. And if we write this in big O notation, we can say that that is big O of n to the s minus 1, because the numerator is big O of n to the s and the denominator is n. So we have that d choose S equals big O of n to the s minus 1. And that implies that d equals big O of n to the 1 minus 1 over s. And now we can use the fact that the number of edges in our graph, the cardinality of E, is equal to big O of n times d. And combining with what we see in the previous bullet, we get big O of n to the 2 minus 1 over s. And that's the bound that we were trying to prove. So that is the best known upper bound on KRS free graphs up to a constant factor. And we'll discuss more about Turan extremal functions of complete bipartite graphs in class. So, thanks for watching.